So I want to demo how we can actually use Ampere-Maxwell law to get a result we're pretty familiar with. Let's say we want to find the magnetic field at point P due to a line of charge, right? Like a finite, keyword finite line of charge. When we use our regular Ampere-Maxwell law, where we're saying that, hey, we're going to take, we're doing it in terms of A being half the length, x initial being the distance from point P to the center of the rod. When we do our usual Ampere's law, right, B dot dl is going to equal mu naught I enclosed. We're saying, hey, we're going to make an Amperian loop sort of like this, which is circular with a radius x initial to use symmetry. And when I use symmetry, the magnetic field along this point I know is going to be the same everywhere along that point. So point being dl, right, on every dl along that loop. So I can pull b out of the integral. So I'm really doing b integral dl is going to equal mu naught I being the current. And then I just say, hey, well, my loop, the length of the loop, that's what I get by integrating dl. It's going to be 2 pi x initial. And I get my classic result. So we're going to see why this equation is not true for a finite line of charge, right? In reality, this isn't true. You actually have to use Biot-Savart law to get the exact result. So I'll just write this from Biot-Savart. The actual result is the same thing, but now we're multiplying by a over square root a squared plus x initial squared. So we're going to see how the Ampere-Maxwell law gives us the same result. What do we kind of need for Ampere-Maxwell law? Well, for Ampere-Maxwell law tells us that changing electric fields, specifically changing electric flux, can actually create magnetic fields. And current, well, how do you get a changing electric field from current? Because, in reality, there is an electric field, going through this wire. We're going to assume it's basically negligible. In reality, what's happening is, well, if you're having current coming from the bottom to the top, well, that's positive charge moving. You're going to end up with some negative Q charge here, where the positive charge has moved up to the top. And over time, the charge, the negative and the positive, will actually grow in size, right? It's going to get stronger. There's going to be more charge. So the electric field by those charges are going to change. And those electric fields going through the loop, that's flux. The flux is going to change over time. Ding, ding, ding. That's Ampere-Maxwell law. So if we write out Ampere-Maxwell law, very similar form, except now we have this mu naught times I enclosed plus the displacement term, the epsilon naught d flux dt. This is not really current, but Maxwell called it displacement current. So we just need to find the flux as a function of time through this Amperian loop, through the path we're going to integrate, and then we can eventually find the magnetic field, right? Once I find the flux and the rate at which it changes. So let's just find the flux, right? Well, to find the flux, it's actually kind of crazy because if you think about a point charge, positive Q, right? It's going to have field lines radiating pretty much radially, right? So it's going to pass through this loop. And to find the flux, the electric field here is different from the electric field at this point because the distance is slightly bigger farther away from point Q. And the angle, right? Remember, flux is, the electric flux is EA cosine theta, right? It's a dot product, so the angle changes. So we gotta take the integral, right? Unfortunately, we have to we have to, or if you're into this stuff, fortunately, you're gonna have to take the integral E dot dA, or specifically integral EdA cosine theta. So if I want to do that, what I need to do is, well, what's my dA? Well, my dA, if I draw it in, my dA, I really want to integrate through radius. There's probably maybe a better way to do it, but I want to integrate through radius, and my dA at any radius is going to be this ring, right? It's going to be this ring of area. Well, what's the area of that ring? If you were to unravel it, it would really become a rectangle for very, very, very small dAs. And that rectangle actually has a length, 2 pi r, right? Being the circumference of that ring when I unravel it ends up being the length. And the thickness of that is actually my dr, right? How far I've kind of traveled, I guess, along the ring, right? The change in r. So that's actually the area. dA is going to equal 2 pi r dr. So then what I can do is, now, I wanted to do it in terms of r, by the way, because my electric field at any point is going to equal kq over the distance squared, right? Well, the distance squared, well, the distance would be like a distance like here, right? Well, this is just the point of the positive q. The vertical distance would be positive, like this length right here, right? Positive q to the center of our circle. That's just a, right? That's just half the length. And the horizontal distance would be r, right? It would be, well, at what point, at the radius at which kind of integrating at, or like the point at which like it's just the r, right? While I'm integrating, r ends up being that leg of the triangle. So I have r plus r squared. Pythagorean theorem, right? D squared equals a squared plus r squared. Now the last missing piece is the cosine theta. The cosine theta is going to be changing, right? That theta, the angle in between, I'm going to draw this, I guess I can draw it like this. The angle in between the area vector and the thingamabob is this. What is the angle? It's going to be this angle right here, right? That's the angle between the area vector and the electric field vector, because the area vector is always normal to the surface. Well, that's this angle theta, thanks to vertical or symmetric, I don't know, identical interior angles, I don't know. By geometry, those are the same theta. So the cosine of this theta is always going to be a over square root, right? Adjacent over hypotenuse, a over a squared plus r squared. So when I multiply that by the electric field, basically what I get is this integral kq over a squared plus r squared times 2 pi r dr for the dA term times a over root a squared plus r squared. And this is going to be the integral. And I got to set my bounds here, right? So my bounds, I'm integrating from 0 to x initial. So I get 2 pi kq times a times r dr over a squared plus r squared to the 3 halves. This a squared plus r squared to the 3 halves term. It's an integral that's haunted us since electrostatics. You can actually evaluate. This one's actually not too bad to evaluate. You can actually do u sub, but you eventually get when I take out this whole integral, I get 2 pi kqa, and then I get 1 over a minus 1 over a squared plus x initial squared. This is the result I get from this integral, and that I'm not finished though yet, because I actually need to understand two things. One, this is half of the actual electric flux, because this negative Q is providing an electric flux in the same direction, right? Now, instead of electric field lines starting from Q and going into the area, you have field lines that are going into Q. Well, if you're going into Q, you're piercing through the loop, right, in the same direction. So it actually is double this, right? This is Q's contribution. Negative Q's is the same thanks to symmetry. And you can prove it too, but I'm not going to go do that. But this is also a negative term, right? Because the electric field is really opposing the current. The current's going up here, and the electric field is in the opposite direction. The flux is really negative, right? If you think about it as like the area vector is in the same direction as the current, so the electric field is causing negative flux because it's going the opposite direction. So this is really 1/2 the total flux. So the total flux ends up being negative 4 pi k qa over times this really weird a squared plus x initial squared term. And you would take that integral. So now I just got to find d flux dt. Most of these variables are constant with time. The only thing changing is the charge. So I'm just going to do my 4 pi k qa 1 over a minus 1 over root a squared plus x initial squared times dq dt. Well, hey, dq dt is just current, but you also gotta it's current by definition, but also you make it make sense, right? Because just because this is dq dt over here, so I guess maybe technically it's not really. How do I explain this? We use dq dt for the amount of charge passing a point. Well, this is the amount of charge accumulating at a point. But why is it still dq dt equals current? Well, the current, right, is going to bring a certain amount of charge, a certain amount of dq over small time intervals dt. So over an entire time interval, it just ends up equaling, like the dq to dt just ends up equaling the current. If that makes sense. I think I'm just overcomplicating. You can just think of it as current. Whatever, who cares? Just ignore what I said there. This just ends up being current. So this is kind of magical. Look what I'm about to do. I'm going to take so I'm just going to draw a little line. I'm going to take my integral b dot dl. It's going to equal mu naught I enclosed, which is I, minus epsilon naught, just so I can account for the negative, times 4 pi k. So 4 pi k qa over a. So I'm distributing the epsilon naught to each term. So the first term, and I have to multiply by I. Okay, I'm going to take this term, multiply it to each of these fractions. So times I. Whoops. And then I'm distributing epsilon naught to there. I know I'm skipping some algebra. I just want to make this quick. But you follow along at home. Epsilon naught 4 pi k qa over root a squared plus x initial squared. Well, hey, take a look at this. The 4... Oh, I forgot I put a q here. Whoopsie, I didn't mean to do that. My fault. I meant current. Here's what's kind of magical. 4 pi k. By definition-ish. I guess not right by definition, but Coulomb's constant is 1 over 4 pi epsilon naught. Or epsilon naught equals 1 over 4 pi k. So I'm doing 1 over 4 pi k times 4 pi k. Cancels out. Hey, the a also cancels out. So what I'm left with when I cross all of this out is I'm left with I minus I. That's going to equal 0. And I'm going to just pull this out right now. And then what I'm going to get is, well, now I have I times a over that weird radical. Take a look. When I divide both sides by 2 pi, I get b is equal to mu naught IA over 2 pi x initial times square root x initial squared plus a squared. This is my Biot-Savart result. It is kind of cool that both, by Maxwell's addition makes his law kind of more useful, kind of more applicable. You couldn't really use Ampere's law in this case, but now you can, thanks to that Maxwell guy. So hopefully this video was kind of cool. Thank you for watching.